This is lecture 2C1 on the proof of the linearity of the limit operator. Taking the limit is a linear operation. In the book, this is expressed over several of those limit laws. First, you have the addition and subtraction laws. They state that if you have f with some limit L and a function g with some limit m, that if you add f and g and take the limit, the result is L plus m. If you subtract f and g, the result is L minus m. Then you have the constant multiplier law. In the constant multiplier law, if the function f is multiplied by constant alpha, then the limit is alpha L. I'm going to take those three laws and write them as one law. So here's the one law that I'm going to write. Work with this. It says that the limit of alpha f plus beta g is alpha L plus beta m, where alpha and beta are arbitrary positive constants. I'm restricting alpha and beta to be positive constants so that I don't have to write so many absolute value signs. It's just a matter of convenience. Now, the precise definition of a limit requires that for every epsilon there is a delta such that, and here's my function, alpha f plus beta g, minus the proposed limit, alpha L plus beta m, is less than epsilon whenever x minus x naught is less than delta. The first thing I'm going to do is rearrange everything inside the absolute value signs in that statement to look like this. I'm going to put f and its limit L together, g and its limit m together, and factor out the alpha and beta. Then I'll use a triangle inequality. The triangle inequality states that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And I'll identify alpha times f minus L as the a, and beta times g minus m as the b. Then I can break it out into these two absolute value terms and factor out the alpha and beta. They're positive, so again, we don't need any absolute value signs on alpha and beta. By the definition of a limit, since L is the limit of f, then for any epsilon, we can find a delta. So I'm going to choose the epsilon to be the epsilon from the problem up here and divide it by 2 alpha. So if I set this for my limit, f minus L is less than epsilon over 2a, then I would be able to find a delta. It's guaranteed by the limit law, and I'm going to call that delta delta 1. I'm going to do the same thing for g and its limit m. I'll say g minus m is less than epsilon over 2 beta, and I can find a delta that satisfies that, and I'll call that delta delta 2. And now we're done. Okay, I'm going to let the delta be the minimum of delta 1 and delta 2, the smallest value. All right, and say that for x minus x naught less than delta, I have the following. Okay, here was the statement after I rearranged it. Alpha times f minus L plus beta times g minus m is less than or equal to the two terms broken out. Okay, I factor out the alpha and beta, and using the result from the limit law, I say this is less than alpha, and here was the limit I chose for f minus L, epsilon over 2 alpha, and plus beta, and here's the limit that I chose for g minus m, which is epsilon over 2 beta. That result is epsilon. So for getting all those in-between steps, here is the result. Okay. Alpha f plus beta g minus the proposed limit alpha L plus beta m is less than epsilon, epsilon being arbitrary, for absolute value x minus x naught less than delta. So there's the precise definition of the limit, and that proves the linearity of the limit operation.